Welcome to Lecture 6, Rotational Dynamics and Energy. Rotation of a rigid object about a fixed axis. Angular mechanics. So we've already seen the arc length formula, and you know this from first year math and first year physics as well. So the arc length traveled by a particle that's rotating around a circle and does rotational angle theta is r times theta. You multiply by the radius by the angle that it changed through. The angular displacement is just the change in angle. The instantaneous angular speed or angular velocity is omega is d theta by dt, the rate of change of the angular position with respect to time. And angular acceleration is the rate of change of that with respect to time. So the second derivative of position with respect to time. Equations of angular kinematics. If we've got a constant angular acceleration, then you can use these equations just like we could for linear kinematics. The same calculus derives that. Converting from linear to angular is just a matter of multiplying by the radius. This works in kind of a global sense if the radius is constant, and even if the radius is changing, it still works locally, so for the instantaneous radius at that time. Moment of inertia of a system of particles. Moment of inertia is kind of like the mass, but for angular motion. So moment of inertia is the sum of the mass times the distance r from the rotation axis squared. The moment of inertia, you have to specify about what axis. It's not the same for one axis or another one. It's easier to rotate things about certain axes. Rotational energy is a half I omega squared. So if the object is rotating with angular speed omega about the axis about some axis for which its moment of inertia is I, then half I omega squared, just like half mv squared is the linear kinetic energy. Moment of inertia of a rigid body. So if we've got an extended body, then the moment of inertia formula that's a sum just becomes an integral, not surprisingly. Torque associated with a force F acting on an object is Fd. So the torque, if D is the moment arm of the force, and this only works if the force is perpendicular. In general, you have to use a cross product. We'll see that a little bit later. The torque, the net torque acting on an object is I times alpha. So the moment of inertia times the angular acceleration. Parallel axis theorem. The moment of inertia, if you know it through the center of mass and you want to know the moment of inertia spinning it about a different axis that's parallel to that one, then you can get that new moment of inertia from this formula called the parallel axis theorem. It says that if you displace the axis by a distance d, then the new moment of inertia is the one about the center of mass plus the total mass of the object times the displacement of the axes squared. The moment of inertia then is always smallest about an axis that goes through the center of mass. You can see because this thing's always positive, so if you go about a different parallel axis, then it gets bigger. Be careful that there's lots of different moments of inertia for an object, even through the center of mass, because there's lots of different axes that you could rotate the object through, except for a sphere, where any axis pointing through the center of mass would have the same moment of inertia because of spherical symmetry. For other objects, if you were to take an axis through the center of mass and then imagine that you were to not translate but rotate that axis through some angle, then you'd have an axis that still could go through the center of mass, but would give you a different moment of inertia. So a cylinder maybe has one axis if you're going to be one moment of inertia if you're going to be spinning it about its axis, and another moment of inertia if you're going to be flipping it over end to end. If you're going to be rotating an object about a fixed axis, then you're delivering power to it given by the torque times the angular velocity. Just like power was force times the velocity, power for rotating is torque times the angular velocity. And we've also got the rotational work kinetic energy theorem, that the work done on a particle is the change in its rotational kinetic energy. This is if all the work is going into rotating the object. Spinning masses. We've got these two masses, m1 and m2, and they're rotating together with this angular velocity. We want to know what the ratio of the tensions is. This is a problem that we could have done earlier. It just requires the v squared over r, but now we're going to look at it in rotational language. We're going to be concerned with the angular velocity rather than figuring out the linear velocity of these. Okay, so v squared over r, using the fact that the velocity is r times the angular velocity, we can write what the centripetal acceleration is, what the radial acceleration is, in terms of omega, which is useful because omega is the same for both of the masses, unlike the velocity. If we let big R be the 60 centimeter radius of the inner one, then we've got that tension 2 has to equal m2 times its radial acceleration, m2 2r omega squared. And for m1, the net force is t1 minus t2, and that would be m1 r omega squared. Combining these and setting the masses equal, we can come up with an equation for what t1 is and t2. So the ratio between the tension 1 and tension 2 is 3/2. T1's larger because it's holding on to both of the masses, but it's not double because the net force that's required to move this mass in the bigger circle with the same angular velocity is larger. And so mass 2 needs twice as much net force on it as mass 1 does. Now we're going to take 3 questions to calculate some moments of inertia. So we've got 4 identical particles, 1, 2, 3, 4, and they're connected by these massless rods to form a square. These particles are all the same mass, and we're asked what is the moment of inertia of this system through this diagonal axis that goes through this particle and this particle. So we're going to be spinning it about that axis. This piece would be spinning to there and back like that. And then we want to find out what the moment of inertia of the system is through the parallel axis that passes through the top left particle, parallel to this axis. So if we were to move this axis over to here, so that it's this way now, and then spin this object so it flips like way up around that, and this one's kind of moving up and down like that, well, around this axis, then what would the moment of inertia be? All right, so we're going to use our mr squared formula, adding that all up. We just need to figure out how big the diagonal is, and if this is side d, then the diagonal is √2 times d, and so from there to the axis is 1/2 of that, so 1/2 of √2d, m plus the sum of the distance away from the axis. This one's 0 away, this one's 0 away, this one is 1/2 of √2 times d away. Adding all of that up, we get md squared. For the second one, we can use both the parallel axis theorem and this formula directly. Give that a shot. Either way, you come up with the same answer. So using the formula directly, but with the different distances, it's 3md squared. Parallel axis theorem, remember that it's the total mass times the displacement of the axis squared, plus the moment of inertia through the center of mass, 3md squared again. Distributed mass moment of inertia, calculating the moment of inertia of a rod. We're going to calculate the moment of inertia about one end because that integral is a little bit easier. So find the moment of inertia of a uniform mass per length equals mu. So the mass per length is mu, and it's a rod of total length L about one end in terms of its dimensions and its mass. The trick is to write the contribution to the moment of inertia about this axis, about the end, the axis through the end, from this little piece dm. And that would be I is, a little bit of moment of inertia is x squared dm, where x is the distance from that axis. Then we'd find the total moment of inertia by just integrating that. dm is mu times dx. And so we come up with 1/2, or rather 1/3 of mu L cubed. But mu L is equal to the mass per length times the total length, so 1/3 ml squared. Familiar result for moment of inertia about the end. If we want the moment of inertia about its center of mass now, we can again proceed like we did in the last question and try to get it directly, or using parallel axis theorem. So directly would just be to substitute in different boundaries. So we'd have negative L over 2 and positive L over 2 here. Using parallel axis theorem, we just displace it by an L over 2, ending up with 1/12 ml squared. So how much easier is it to spin the rod about the center than the end? 4 times easier. The moment of inertia is 4 times higher about the end than it is about the center. Distributed mass moment of inertia for a solid cylinder. Find the moment of inertia of a solid cylinder, uniform density rho, so a solid cylinder with uniform density rho, length L and radius R, about its cylindrical axis, the one that goes through the center here, so the edge of the cylinder looks like a circle, in terms of its dimensions and mass m. Well, here's our mass element here. It's a little bit of a cylindrical shell, just like you did in cylindrical shells method in first year with some volume integrals. What we've got is a distance r away from the center for this piece. So if we're spinning it about that, then all of that is at the same, so about the central axis of the cylinder, this whole band has the same distance, and so it's useful to use for the moment of inertia calculation. The little bit of mass is rho d volume, and volume is L 2 pi r dr. This is the little bit of volume of this thing of thickness dr. Has a surface area 2 pi r. Just imagine that you were going to unwrap that. That's the circumference. So surface area 2 pi r times the length, which is in and out of the page here. Moment of inertia is integral of r squared dm, and dm, as we have above there, integrating the r cubed gives us an r to the 4 over 4, substitute into the r, and the 0 goes away. Then we're left with this result. If we were to sub in the fact that rho times the volume, this pi l r squared, pi r squared l is the volume, is that combination is the mass, then we can write it in terms of what we wanted to write it in terms of the mass. So we're left with half mr squared. You may remember that from first year. Now we're going to imagine that the cylinder isn't solid, but instead is hollowed to an inner radius r in. So instead of starting at the center, our integral would just have to start at r in. Find the new moment of inertia in terms of the mass. Finding the new moment of inertia in terms of the density is not too bad. You just change the lower bound of the integral, but finding it in terms of the mass is a little bit trickier, so give that a shot. Okay, changing the lower bound of the integral, the new moment of inertia is this. And now the mass is not the same as it was earlier. We're left with integrating rho L 2 pi r dr. You could kind of use the same, just the mass element, and integrate that rather than integrating it times r squared like we did to get moment of inertia. So we're left with the mass being given by this. That kind of makes sense. It's like rho L times the area of what the outer circle would be minus the area of the inner circle, because that's the difference in the area. So multiplying the new surface area by the length and the density will give us the new mass. If we factor the moment of inertia into this thing being a difference of squares, lets us say, okay, well, that's the difference of the square root of r to the 4, which itself is r squared, times the sum of the square root of r to the 4. Then we're left with saying, this thing in front is the mass. So we've got 1/2 m big R squared plus r in squared. Let's check that it works. So if we were to substitute in r in is 0, then we get 1/2 m big R squared like we had last time. And if we were to put in that the inner radius is equal to the outer radius, which is the extreme case of all the mass being concentrated at the edge, we've got just a ring in that case, then you'd expect the moment of inertia would just be the mass times the radius squared, because it's all at that radius. Sure enough, if we put that in, then we've got 2r squared here, cancels with the 2 in front, and we get mr squared, which is the limit of the ring. Okay, so concept question, think about this for a bit. If you hollow out a cylinder, then you increase its moment of inertia. Well, that's false, actually. You increase its moment of inertia relative to its mass. So if you look at this, it looks like if you make the r in bigger, then you increase the moment of inertia. But if you're hollowing out the cylinder, you don't just increase r in, you decrease m at the same time. It's better to use this formula in terms of the density if you're hollowing it out, because then the density stays the same even though the mass changes. So this is a better formula to use. You can see that as r in gets bigger, the moment of inertia gets smaller. So a concept question based on that kind of idea. Two solid steel cylinders have the same density and length, but have different diameters. One's twice the diameter of the other one. What's the ratio of their moments of inertia? You have to be careful again using half mr squared, the cylinder one, because the bigger one also has a mass increased by a factor of 4. So you get 2 factors of 4 or a factor of 16. Alternatively, you could just use the one in terms of density, which tells you that the moment of inertia scales with r to the 4 for a constant density, and we've got 16 times the moment of inertia for the steel cylinder with double the diameter. Final question for today, block on a ramp with a non-frictionless pulley. So the pulley is not frictionless, the rope is going to be staying connected to it, and in fact the pulley's axle has some friction in it too. So the block has this mass, 2.5 kilos, and it slides down a frictionless ramp angled 35 degrees to the horizontal. Ramp is frictionless, but it's attached to a light cord wrapped around a wheel with a known radius, and the block accelerates at 2 meters per second squared down the ramp. There's no friction between the block and the ramp, but again, there is friction in the wheel's axle, which applies a constant frictional torque of 0.4 Newton meters to the wheel as it unwinds. Find the tension in the rope and the moment of inertia of the wheel. So here's a free body diagram to help with that. The first part, you can figure out the gravity force down the ramp. A great way to think about this is I like to imagine the angles opening up from 0, and so here's the weight pointing down, mg, and the construction that you'd use to break the weight up into its components perpendicular to the ramp and parallel to the ramp. And then imagine that this ramp angle decreases towards 0, like the ramp closes, and see what would happen to this thing. This should close as well. That's how you know that they're the same angle. If you can also picture them opening up to 90 degrees, and this one also opens to 90 degrees. So it is the right kind of angle, similar triangle setup there. All right, the force on the block perpendicular to the ramp we can use to calculate the normal force, but actually we don't really need this because the ramp is frictionless. If the problem were to change so that the ramp did have friction, then that would be important. But in this particular case, it's a little bit easier. We don't need the normal force because there's no friction on the ramp. Force on the block down the ramp then doesn't include a friction component. It's just mg sine theta, sine 35 degrees for this component of the weight down the ramp, minus the tension in the cord, is equal to the mass of the block times its acceleration. And that's the equation that lets us solve for the tension. That's one of the two things we needed to find here. Before we go further, we need to relate the angular and linear acceleration of the block. The angular acceleration is the linear acceleration divided by the radius. So we know that the linear acceleration of the block is related to the angular acceleration of the pulley, measured in the counterclockwise direction through this equation. And so the torque on the wheel in the counterclockwise direction would be radius times the tension minus the frictional one that opposes the motion of the wheel is equal to I alpha. Substituting in what we found earlier, we can come up with the moment of inertia. Okay, let's analyze this. There's 3 different terms here. There's this sort of r squared m g over a sine 35. That seems to depend on gravity and the angle, as well as the block mass and some radius things. And then we're subtracting off from that r squared m, which looks like it's just kind of a relationship between the wheel and the block mass. And then we're also subtracting off this friction term. So if there's more frictional torque, then we would need less moment of inertia, and vice versa. Let's think about this. What's going on in this problem is we've got gravitational energy in the block being converted into what? Into kinetic energy in the block, into rotational energy in the wheel, and also into frictional energy, into losses in friction, into heat in the axle. So if this first term here is the gravity energy, and that would increase the moment of inertia because moment of inertia increases the kinetic energy in the wheel. The second term is related to the kinetic energy of the block. So that's a decrease. If the block's getting more energy, then the moment of inertia doesn't need to be as big. And then this term here is the frictional energy. So if friction were higher, then more energy would go into that rather than the wheel.